All right, as I began to say, we're not going to do a ton with the atomic properties. All the things we're going to lay out in this class were discovered before people discovered the atom. So you don't need the idea of an atom or an electron to think about this stuff in this class. However, since we do know about atoms and electrons, charge has an unusual property that it doesn't come in arbitrary sized pieces. Every piece of separable charge you find is an integer multiple of fundamental charge. That's the law of quantization of charge. So it simply says that electric charge comes in integer multiples of the fundamental charge E. So, got to tell you what E is. Fundamental or the quantum of charge is 1.602 times 10 to the minus 19 coulombs. So quite small, not many coulombs. And this law of quantization of charge means that any charge Q can be written as some integer times E. And the integer can be positive or negative. We can have positive or negative charges. So, probably been looking at particle physics a little this summer because of the Higgs boson. Almost all the charged particles you ever have to deal with are formed of protons whose charge is positive E, electrons whose charge is negative E, and neutrons that are neutral. So all those other things, the strange quarks, the muons, are really only produced in cosmic events or in particle accelerators. And so these things make up all the charged matter you guys deal with. Okay, I said it was the most important feature in most processes, so it'd be kind of nice if it stayed around, and it does. So charge is conserved. So, our second physical law is the law of conservation of charge. And this just says the total charge before something happens is equal to the total charge after it happens. Or the total charge before a process is equal to the total charge after. All right, or symbolically, if we add up all the charge before something happens, it's the sum symbol. We get the total charge after that thing happens. Okay, this doesn't mean you can't make charged particles. In fact, you've got something in your house that happily makes charged particles for you. Most of you have a smoke detector. Hope. Inside most household smoke detectors, a small amount of radioactive material, usually mercurium, that takes neutrons through the process called beta decay and turns them into protons, electrons, and a weird thing called an antineutrino. So, this neutron, which is neutral, is happily making charged particles, protons and electrons. But if you could add up the charge before, neutrons are neutral, and the charge after, this is plus E for the proton, plus a minus E for the electron, plus 0 for the neutrino, you find the charge before is the charge after.